Okay, so this summer I worked on how river flooding impacts nutrient cycling in floodplain features, as you can see up on the screen. And I primarily worked under Dr. Hassenmuller and Dr. Sloan, and I spent most of my days over at the lab at SLU. And so to start off, I really want to explain the eutrophication problem in as much detail as I can at the moment. So what is eutrophication? I know a few of the other interns mentioned this in their presentations, but just to give everybody a refresher in case anybody doesn't know, basically what eutrophication is whenever a body of water receives a large influx of nutrients, that causes all of the algae to grow a bunch because they have a bunch of food available to them. And then once they grow and grow and grow, they all die off eventually, and whenever they die off, they respire and they take in oxygen from that system, which leads to hypoxia, which is a state when the water column is almost completely depleted of dissolved oxygen, which leads to basically everything else there, again, unless it can breathe anaerobically, to die off or experience significant health impacts. And again, the nutrients are the reason why those algal blooms will happen in the first place and why we have eutrophication. And you can see some of those negative impacts with the fish kill that's up on the top right, and then also just some examples of algal blooms on the bottom right. And it can occur in estuaries, which is where the river meets the ocean. And I specifically focused on the Mississippi River estuary throughout the summer. And it can also happen in coastal waters in general and lakes and reservoirs. And the water usually needs to be warm, stagnant, and again, really nutrient rich. And then I'd also like to briefly explain non-point versus point sources because this was also important to my research. So point sources would be, for instance, like a paper mill on the river where you can go there and you can see, okay, this is the nutrient output of this paper mill. Versus non-point sources would be something like, for instance, a backwater area that releases more nutrients whenever it floods. And there's a bunch of those along the river, so you can't really go to like each specific one and conduct a bunch of studies there and be like, this is the exact impact that each one of these areas is having. And so I'm sure some of you are wondering, why should I even care about this? Like maybe this doesn't impact me at all. Bad news, it does. As you can see from the map on the right side, they measured human footprint and then also looked at where hypoxic systems are. And as you can see, they're pretty ubiquitous throughout the world, especially in the northern hemisphere. So we are pretty heavily impacted by them. And they have both human and environmental impacts. And so to go down some of the human impacts, cyanobacterial blooms can be really harmful, especially if they release cyanotoxins. And those that whenever they reach dangerous concentrations, they can cause a myriad of health issues ranging from conjunctivitis to atypical pneumonia to vomiting and a bunch of other horrible stuff. And then in terms of ecosystems and biodiversity, they can significantly disrupt the food web of these areas, leading to a loss of biodiversity and also, as you saw in the photo in the other slide, massive fish kills. I actually experienced one of these like yesterday. I was walking in Lafayette Park in St. Louis, and it was this really pretty lake, and then if you went over to the other side, there was a little island where they had a duck coop, and there were just like a bunch of dead fish all over there from all the nitrogen from the waste of the ducks. So our big question this summer was, how do floodplain features along the Mississippi River experience changes in water column nutrient levels during flood events? And we specifically focused on the Alton Slough, which you can see in those yellow push pins that are on the maps right there. And as you can see on the left, usually the slough looks all good, like there's nothing really going on. You can see Ellis Island in between there and the river, so it's pretty separated from the river usually. But as you can see on the right side of the screen, whenever a flood event occurs, like it completely changes the dynamics in that area to the point to where you can barely even see Ellis Island anymore. And at that point, it's really, really heavily impacted by whatever's happening on the Mississippi River, which can change the nutrient dynamics. And something also important to note here is that whenever we were looking at this area, we were specifically looking at the nutrients that would usually be sequestered in the soil, and we wanted to see if during a flood event, those would move into the water column and then end up creating more pollution in the river, going downstream and contributing to that hypoxic zone in the Gulf of Mexico that I'm sure at least some of you guys have seen on the news before. So, our methods. So first we obtained and homogenized the samples during a sampling trip to the slough. For this we used what I like to call the Sloan anchor method. In other words, our PVC pipe corer would not work with the sediments there, so Dr. Sloan just threw his anchor down and we took up the sediments that were brought up with that, mixed them all up in a bucket with a spade, and then put them into these big plastic tubes that you can see right beside me in the photo on the far right. And so then we had 3 different treatments, and we just randomly picked the cores for these treatments. We had characterization, which was basically our control, where we just had the sediments in that core tube. We cut them up into 3 different sizes, and then we tested and analyzed each one of those depths for what their nutrients looked like. And then we had diffusion, which was supposed to represent the normal conditions of the slough, which you can see again at the bottom left. And then those were also placed in the cores, but they received a layer of water on top of them that we gathered from the river. And that was replenished whenever we took out water for our nutrient samples. And those were just locked away into a cabinet for 2 weeks. We would just take them out once a day to sample them. And other than that, they just stood there in complete darkness, untouched. And then we had our advection samples, which represented the flooded conditions that you see in the left corner, but on the right side of the normal map. And for those, we did the same thing as the diffusion cores, but instead of just leaving them in a cabinet for 2 weeks, we put them into a shaker, and so they were just continuously shaken up, aside from us taking them out to sample them over the course of those 2 weeks. And so we had a daily sampling procedure over the course of those 2 weeks, including on weekends. So we would come in, we would get water data, so we would look at like dissolved oxygen, pH, conductivity, all of those different factors that you could use. We used a Pro Plus to find those, and we also used a turbidity meter to check the turbidity of the water, which is really important for comparing our diffusion and our advection cores, because there were a lot more particles floating around in the advection cores. And then we also got a water sample from each core every single day, and those were sent off to the lab here, and we analyzed those for nutrients. And then we also did DDI extractions from the pore water, so that was looking at the actual sediment and looking at whatever nutrients might be in the pores of that sediment. And we did loosely bound, or KCl, nutrient extractions, which looked at the surface of the sediment to see what nutrients were there. And again, analyzed all of those on a discrete analyzer. So in terms of our analysis results for the core water columns in particular, I want to start off by directing your attention to the dissolved oxygen on the top left corner. And that's just to kind of show that the conditions, like first and foremost, between the diffusion cores and the advection cores were very, very different over the course of this. As you can see, the diffusion cores, which are indicated by the blue, had this pretty significant dip in dissolved oxygen, and then at the end of the experiment, it came back up a little bit. We're not sure why that happened, but they had that dip versus the advection cores, because they were being shaken up the entire time. The oxygen levels stayed pretty much the same. And you'll also notice the green replacement water. That was the water that we took from the river, and so we just wanted to also test all of the variables with that to see how that was comparing to the other two, to see if the replacement water was having any impacts. And then if we look at the phosphate, which is directly below that on the bottom left corner, this is where we saw some really significant results, because for some of our advection data points, you'll notice that they are significantly higher than the diffusion, and for some of them, they were significantly above the Illinois EPA drinking water standard of 0.05 milligrams per liter of phosphate. So there was some pretty nasty water there. It got pretty gross, versus the diffusion cores didn't get anywhere near that high. And then if we look at nitrate, again, like the advection cores, as you can see, were significantly higher than the diffusion cores in terms of their nutrient load. And for ammonium, we noticed that the diffusion cores drop-off of ammonium was a lot slower than it was in the advection cores. And then in terms of our results for our sediment samples, we did see a difference, but it wasn't necessarily statistically significant, as you can see by the error bars. But we did see that the characterization cores, which represented like the before for the entire experiment, did have like fewer nutrients in most cases than the diffusion and advection cores that had received those treatments afterwards. So in terms of the interpretation, we did find that flooding tends to increase nutrient release from sediments in normally quiescent sites, which was like a pretty big finding in terms of like we showed, at least in this study, that those areas that usually just aren't really impacted by the river like do release more nutrients and contribute to that pollution more whenever you have these major flood events. The nutrients released from sediments by flood events may raise concentrations in the water column to levels significantly higher than regulatory limits, as I mentioned with the phosphate, and sloughs and backwater channels along the Mississippi River, similar to the study site, may also serve as sources of pollution whenever they experience these flood events. And these flood-related nutrient releases, as I stated at the beginning of the presentation, have impacts on human and ecosystem health, both where they're located and then also further down the watershed. Oh, and I'd also like to acknowledge, thank you, Dr. Sloan and Dr. Hassenmuller, for all of your help this summer, and also to Tracy and Josh, the other intern, who came in a ton to help me out on the weekends when I was running this, and also to all of the other members of the lab that helped out with this experiment. I really appreciate it. So yeah, any questions? Yes.
You had mentioned early on that one of the reasons why the algal blooms got so out of control was because of all these ducks were expelling nitrogen everywhere. Would that mean that like these ducks could potentially be considered like invasive in a way if they're ruining everything else?
I think that's more like poor park management in general in that specific instance. Any other questions? Yeah.
The nutrients that were trapped during the flooded site, how did they get there in the first place? Were they deposited first before?
Mm-hmm. So I wouldn't know the history super in depth, but I would assume based off of the area as a whole that they were likely the result of agriculture, since that's really prominent in this area. There might also be some industrial impacts as well. And also the slough in general it's a dumping site basically. Like in multiple of our sediment samples, we found like screws and like shards of glass in there. So there's a lot of human influence on that site in general. Anything else for me?
There is a question from Dr. Danielle Page, and she said, would these sources during flooding be sinks at regular flow?
So something that we wanted to look at, but we didn't have time to, was we actually, with the advection cores that represented the flooding, we also wanted to take like a week or two after that to allow them to return to those diffuse conditions to see if that would change the nutrients and if they would be like resequestered into the sediments or not. And Josh actually kind of tackled that question with his research, so I'll leave that to him to talk more about, but I didn't really go super in depth into that in my research per se.
Yeah, I want to echo that question as well, because if you do a mass balance on it, the phosphorus has to come from somewhere before it can be released. So it will be interesting to find what is the source.
Yeah,
is
absolutely.
From depositing earlier and then re-releasing it. So then if you say it's a point source, but it's a point source at different times because it's a sink at another time. Right? So it might be more of a timing issue than of a net gain in phosphorus.
Yeah, like I said, didn't really get to look at that in this study, but that would be like, those would be really interesting questions to look into in the future. Anything else?
Dr. Hassenmuller says, great job, Leeza.
Thank you, Liz.